A galaxy can devour its neighbor and show no sign of the meal. This is galactic cannibalism, a silent feast shaping our universe. By the end of this, you will understand the invisible forces that let cosmic giants grow without changing their form. How can a violent collision leave no mark, and what does dark matter have to do with it? What does it mean for a universe to build itself through such quiet destruction? The very definition of galactic cannibalism presents a cosmic puzzle. We picture galaxy collisions as violent, chaotic events that tear structures apart, but here the opposite happens. A larger galaxy consumes a smaller one, and its beautiful spiral arms, its central bulge, and its vast disk show no sign of the trauma. The dominant structure remains perfectly intact. How is this serene outcome possible from such a destructive process? The answer begins with a simple but powerful concept: mass. Experts like astronomer Sandra Faber point to the critical importance of mass ratios. When a massive galaxy, perhaps a giant elliptical, absorbs a tiny dwarf galaxy, the difference in their sizes is staggering. The larger galaxy's immense gravitational field is so overwhelming that it completely controls the encounter. It swallows the smaller galaxy whole, smoothing over any potential disruptions with ease. Think of it as the ocean absorbing a single raindrop. The raindrop vanishes, and the vast, powerful ocean shows no lasting change. This foundational idea, the sheer dominance of gravity, leads us directly to the invisible architect of these events, the mysterious presence of dark matter. That immense gravitational dominance has a hidden source, a cosmic scaffold we cannot see. Dark matter forms vast, invisible halos around galaxies, acting as a gravitational cushion that completely changes how collisions unfold. These halos are not part of the bright, swirling disk of stars we see in images. Instead, they are colossal spheres of mysterious matter that extend far beyond the visible galaxy, containing most of its total mass. When a smaller galaxy approaches, it does not immediately head for the bright center. It first encounters this extended dark matter halo, and the interaction is anything but direct. Think of the dark matter halo as a deep, soft field of snow. If you try to run through it, you sink in and slow down long before you reach the other side. That is precisely what happens to an incoming dwarf galaxy. The halo's immense gravitational pull acts like a cosmic shock absorber, robbing the smaller galaxy of its momentum and energy. It gets slowed down and stretched out in a process called tidal stripping, long before the dwarf galaxy's core could ever reach the central disk to cause a disruptive crash. Its own stars and gas are gently pulled away, streamed into long, faint trails that eventually blend into the halo of the larger galaxy. This is why the visible structure remains pristine. The real action, the violent dismantling, happens invisibly in the dark matter outskirts, far from the beautiful spiral arms. Sophisticated cosmic simulations, like those from the Illustris TNG project, visually demonstrate this. They show that galaxies with the most massive and extended dark matter halos are the ones that can consume others while keeping their iconic shapes perfectly intact. The visible galaxy we admire is merely the jewel at the center of a much larger, unseen fortress, a fortress that does the messy work of consumption so the center can remain beautiful. This silent, distant stripping leads us directly to the next critical condition for a peaceful merger: the sheer scale of the mismatch between the diner and its dinner. This staggering size difference makes the entire process far more gentle than you might expect. When one galaxy is at least 10 times more massive than the other, its gravitational well is not just stronger, it is overwhelmingly dominant. Picture a sumo wrestler effortlessly catching a running toddler. The sheer imbalance of the situation guarantees stability. The larger galaxy's gravity is like a deep, smooth pit, and the smaller galaxy stars simply fall into orbits that already exist within that pit. They are assimilated, not colliding. This means the fundamental dynamics of the giant galaxy, its rotation speed and the random motions of its stars, barely flicker. The new stars add such a negligible amount of mass to the total system that they do not change the underlying rhythm. We see this happening right in our cosmic neighborhood. Our own Milky Way is currently consuming the Sagittarius dwarf spheroidal galaxy. This smaller galaxy is being pulled apart, its stars strewn into long, faint streams that wrap around our galaxy. Yet, the magnificent spiral arms of the Milky Way remain completely undisturbed. The incoming stars are scattered so thinly throughout the vast halo and disk that they avoid any concentrated impact that could warp or distort the grand design. This principle of disproportionate scale is absolutely key to preserving a galaxy's iconic pattern, which makes you wonder, are some galaxy types just better suited for this cosmic consumption than others? The very type of galaxy doing the consuming plays a crucial role in this cosmic stability. Elliptical galaxies are the universe's ultimate sponges for stellar mergers. Unlike the orderly, rotating disk of a spiral, an elliptical is a vast, three-dimensional cloud of stars. These stars do not follow a single, coordinated path. They buzz around in every direction like a swarm of bees. When an elliptical galaxy absorbs a smaller neighbor, the incoming stars simply join this chaotic dance. They are just a few more bees in the immense swarm, and their arrival does nothing to disrupt the overall formless shape. The galaxy's structure is inherently resilient to such additions. Spiral galaxies, however, present a more delicate situation. Their beautiful arms are not solid structures but are actually density waves like spiral-shaped traffic jams moving through the disk. A major collision can scramble this wave pattern, destroying the spiral. Yet they too can be cannibals without consequence, but only under the right conditions. If a spiral like our Milky Way consumes a much smaller, gas-poor dwarf galaxy, the impact is minimal. The incoming stars are too few, and their collective gravity too weak to disrupt the grand spiral density wave. The galaxy's structural integrity acts as a powerful buffer. Astronomers use the Hubble sequence, a classification of galaxy types, to predict these outcomes. Lenticular galaxies, for instance, sit between ellipticals and spirals, possessing a disk but no spiral arms, and they too can absorb small galaxies with minimal visible change. We see this principle in action with our nearest large galactic neighbor, the Andromeda Galaxy. Andromeda has a history of consuming dwarf galaxies, and yet its magnificent spiral structure remains perfectly clear and defined. The galaxy's inherent design endures because the mergers were so lopsided. This resilience is a testament to the stable frameworks that underpin cosmic giants, but the final outcome of any meal also depends on the angle of approach. The angle of approach is everything in this cosmic dance. A galaxy's path toward its devourer decides between a violent splash and a silent assimilation. A direct head-on plunge sends shockwaves through the larger galaxy's disk, violently compressing gas and triggering bursts of star formation that can permanently scar its beautiful structure. But the universe favors a more graceful method, a gradual, tangential orbit where the smaller galaxy swings around the outskirts, allows tidal forces to perform their slow, meticulous work. In this scenario, the victim is not shattered in a single impact but is gradually unraveled over billions of years. The smaller galaxy's own gravity cannot hold onto its outer stars, which are gently pulled away into long, shimmering streams. This is a slow-motion dissection happening far from the vulnerable spiral arms. The orbit's inclination adds another layer to this delicate process. A high-inclination orbit, one that takes the smaller galaxy far above and below the main disk, is especially effective. It spends most of its time in the galaxy's gravitational suburbs, where the tidal forces are just strong enough to strip it but too weak to violently disturb the central structure. This leads to a prolonged and peaceful assimilation. The direction of the orbit is the final piece of the puzzle. Picture two cars merging onto a highway. If one car enters going the same direction as traffic, the merge is smooth. This is a prograde orbit where the smaller galaxy moves in the same direction as the larger galaxy's rotation. The relative speed between them is low, allowing for a gentle integration. But if a car enters heading the wrong way, the result is a catastrophic collision. That is a retrograde orbit, and it injects a tremendous amount of chaotic energy into the system. Computational models show that prograde orbits are the masters of pattern preservation. This orbital harmony ensures the incoming material blends in seamlessly, preventing the formation of disruptive new structures like polar rings or warped disks. The entire merger becomes a quiet affair, a testament to celestial mechanics guiding a peaceful consumption. This graceful dance, however, depends on one final ingredient, the very nature of the material being consumed. The final ingredient for a silent feast is what the consumed galaxy is made of. A meal that lacks gas is a meal that leaves no mess. When a satellite galaxy is rich in gas, its absorption is a spectacularly violent affair. That gas slams into the larger galaxy's own gas reservoir, compressing it and triggering ferocious waves of new star formation. These starbursts light up the galaxy, creating bright, blue knots of young stars whose intense radiation and eventual supernova explosions blast outwards, churning and distorting the galaxy's structure. It is a brilliant, chaotic rebirth that can permanently alter a galaxy's shape. But when the consumed galaxy is gas-poor, the entire process is hushed. Dwarf spheroidal galaxies are the perfect example. These are faint, ancient collections of stars that have long since used up or lost all their free gas. They are cosmic fossils. As they are pulled apart by tidal forces, they release only old, red stars into the larger galaxy. There is no fresh gas to collapse, no starburst to ignite, and no feedback to stir the pot. The new stars simply blend into the existing population, adding a nearly imperceptible sheen to the host's light. We see this principle at work in the dense environments of galaxy clusters, where many small satellites are red and dead, having been stripped of their gas long before their final descent. Their absorption is the ultimate stealth operation, a stellar addition so smooth it barely registers. This quiet assimilation, governed by the properties of both the diner and the dinner, unfolds over a timescale so vast it challenges our very perception of cosmic events. Time itself becomes the ultimate sculptor in these silent feasts. A merger stretched across billions of years is a fundamentally different event from a sudden, violent crash. When galactic absorption unfolds with this glacial patience, the larger galaxy is not assaulted, it is gently fed. It has all the time in the universe to dynamically adjust, allowing its own gravitational forces to smoothly redistribute the incoming stars. There is no sudden shock to the system, no jarring disruption. Instead, the process is one of serene assimilation. The evidence for these drawn-out events is often written in faint, celestial ink. Look into the halo of our own Milky Way, and sophisticated surveys like the Gaia mission have mapped the ghostly remnants of past meals. One famous structure, known as the Gaia sausage, is the vast, stretched-out debris of a dwarf galaxy that was slowly torn apart over billions of years. Its stars now form a subtle, sausage-shaped stream in the galactic halo, a cosmic fossil of a meal consumed so gradually that our galaxy's spiral disk never even noticed. These tidal streams are the telltale signatures of prolonged mergers. They show us a process where stars are not blasted away in an instant, but are patiently stripped over countless orbits, their trajectories slowly altered until they eventually blend into the background stellar population. This slow-motion integration is governed by a powerful principle in physics known as adiabatic invariance. In simple terms, it means that if you change a gravitational system very, very slowly, you can preserve its fundamental orbital structures. It is the difference between trying to suddenly stop a spinning bicycle wheel, which sends it wobbling violently, and gently applying a brake over a long distance, which brings it to a smooth halt. The galaxy's beautiful shape is preserved because the changes to its gravitational field happen on a timescale far longer than the orbital periods of its stars. The system simply has time to settle, to find a new equilibrium without any dramatic upheaval. This extended timeline is the final, crucial condition that allows a cosmic giant to grow without changing its face. It forces us to ask where in the universe are these slow, graceful meals most likely to be served. The environment a galaxy calls home can dictate the very nature of its meals. In the sparse cosmic countryside, galaxies drift in relative isolation, but within the dense, bustling cities of the universe known as galaxy clusters, the rules of engagement change completely. A galaxy cluster is a vast metropolis of thousands of galaxies bound together by gravity, and this crowded environment orchestrates a form of galactic preparation that makes seamless absorption almost inevitable. The Virgo cluster is our nearest example of such a place, a swirling hub of activity where galaxies are constantly jostling and interacting. Here, a smaller galaxy does not simply fall toward a giant in a clean, direct line. Long before its final descent, it endures a process astronomers call preprocessing. The space between galaxies in a cluster is not entirely empty. It is filled with a searing hot, thin gas known as the intracluster medium. As a dwarf galaxy plows through this superheated fog at incredible speeds, the pressure is immense, violently scouring away its own reserves of cold gas. This is like a piece of bread being toasted on all sides before it is ever dipped into soup. It loses its moisture and becomes brittle. Simultaneously, the combined gravitational pull from every other galaxy in the cluster creates a pervasive tidal field, a relentless force that tugs and stretches the dwarf, stripping away its most loosely bound stars. By the time a dwarf galaxy finally approaches a massive central galaxy for consumption, it has already been pre-processed. It is a gas-poor, partially dismantled relic, its most disruptive elements long since removed. It arrives at the dinner table already tenderized, its potential for causing a messy starburst or structural damage almost completely neutralized. The high-speed nature of life in a cluster adds another layer of protection for the central galaxy. Because all the members are moving so quickly relative to one another, direct, slow collisions that allow for deep, disruptive plunges are rare. Instead, interactions are often fast and distant, like ships passing in a busy night. A smaller galaxy might swing by a giant, experience a sharp gravitational tug that pulls it apart even further, but its high speed carries the debris away, preventing a concentrated impact on the main disk. The cluster itself acts as a cosmic blender, churning its members and ensuring that only the most subdued and digestible material ever gets close enough to be absorbed. This environmental conditioning is a masterclass in cosmic efficiency, where the community prepares the meal so the individual can dine in peace. It forces us to look past the galaxy itself and acknowledge the powerful role its neighborhood plays in preserving its iconic beauty. The path a small galaxy takes is its ultimate destiny. To preserve the beautiful structure of its giant host, it must avoid a direct hit on the galactic core. The central bulge and disk are the most densely packed regions, where a concentrated plunge could scatter stars like a cue ball breaking a rack, triggering chaos and irreversible change. But when a dwarf galaxy is captured into a wide orbit, it remains far out in the galactic halo. Here, stellar densities are incredibly low, and gravitational forces are diffuse, acting more like a gentle mist than a crushing wave. In this vast, sparse outskirts, the process of tidal stripping can unfold with surgical precision. The dwarf galaxy stars are slowly pulled away one by one, dispersed over such a colossal volume that they never gather in one place to exert a disruptive gravitational pull. Imagine pouring a single cup of sand into an Olympic-sized swimming pool. The grains spread out so thinly they become virtually invisible, leaving the water's surface perfectly calm. This is the stark contrast to a major merger where the central nuclei of two galaxies collide head-on. Those violent encounters often erase spiral patterns entirely, either creating a featureless elliptical galaxy or leaving behind a grotesquely distorted wreck. By steering clear of the central engine, the absorption process becomes a quiet dismantling in the suburbs, leaving the visible design we admire completely untouched. This delicate avoidance hinges entirely on a fundamental property of motion that governs our entire universe, the conservation of angular momentum. This rotational energy, this spin, is a resource the galaxy cannot afford to waste. Angular momentum plays the silent guardian in this entire process, a fundamental property of motion that must be conserved. You can think of it as the cosmic equivalent of a spinning ice skater. When a skater pulls their arms in, they spin faster to conserve their angular momentum. In a galaxy, this principle governs everything from the orbit of a single star to the grand rotation of the entire disk. When a smaller galaxy approaches on that ideal prograde orbit, it is essentially adding its own spin to the system in the same direction. This is not a disruptive force, it is a reinforcing one. The incoming material carries angular momentum that aligns with the galaxy's own rotation, helping to sustain the very structures that define it, like its spiral density waves or a central bar. It is a gentle nudge that keeps the cosmic wheel turning smoothly. Sophisticated numerical simulations reveal the stark consequences of getting this wrong. When a merger happens on a retrograde orbit moving against the galaxy's spin, it acts like a brake. This cancellation of angular momentum injects chaos into the system, randomizing stellar orbits and often leading to the destruction of a delicate spiral pattern, morphing it into a more blob-like elliptical shape. The conservation of this rotational property is therefore non-negotiable for pattern preservation. It ensures the galactic disk remains a stable, rotating plane, allowing new stars to be seamlessly incorporated into the existing flow without causing turbulence. This stable integration of motion leads us directly to the final actors in this drama, the stars themselves, and how their collective behavior seals the fate of the galaxy's iconic form. The stars themselves must cooperate for this perfect assimilation to occur. When a dwarf galaxy is consumed, its individual stars become new citizens of the larger galactic empire. For the host galaxy's beautiful structure to remain unblemished, these new citizens must follow the local laws of motion without causing a commotion. This is where the concept of kinematic heating becomes critical. Imagine a quiet, orderly highway where all cars are moving at a steady, similar speed. Now imagine a group of new cars merging onto this highway. If they enter smoothly, matching the flow of traffic, the entire system remains orderly. But if they swerve in at wildly different speeds and directions, they force everyone else to brake and swerve, creating chaos and thickening the traffic jam. This is precisely what happens in a galaxy. The host galaxy's disk is thin and orderly because most of its stars are on similar circular orbits, a state astronomers call dynamically cold. If the incoming stars from a consumed galaxy have very different random velocities, they would act like those swerving cars, gravitationally nudging the local stars and increasing their random motions. This process, known as kinematic heating, would puff up the thin disk, destroying its delicate flatness and ultimately erasing the spiral patterns we find so beautiful. But in a peaceful merger, this does not happen. The consumed stars often arrive with orbital properties that are already compatible. They join the traffic flow without ever hitting the brakes. This smooth integration is most likely when the satellite galaxy is itself an old, quiescent system. Its stellar population is dynamically cold and has been for billions of years, meaning its stars are already on calm, settled orbits. When such a galaxy is tidally stripped, its stars are released onto paths that are not too different from the orbits of stars in the host's outer disk or halo. They simply blend into the existing population, their addition so gentle that the overall velocity dispersion, the measure of random stellar motion, remains low. Astronomers can actually trace these ancient meals by looking at the chemical fingerprints of stars. They find distinct groups of stars with similar low metallicity, a sign they formed long ago in a separate, smaller galaxy, now peacefully orbiting within the giant. This seamless stellar integration is the final piece of the puzzle, ensuring that the galaxy grows in mass without sacrificing its iconic form. Yet, at the very heart of this stable system lies a potential source of immense violence, a supermassive black hole. Even the most monstrous black holes can be agents of cosmic stability. At the heart of nearly every massive galaxy, including our own Milky Way, resides a supermassive black hole. These are not the destructive voids we often imagine, but during a minor merger, they can act as a profound gravitational anchor. Their influence stems from an almost unimaginably deep gravitational well, a pit in space-time so steep that it dictates the motion of everything in the galactic core. When a small galaxy is absorbed, its stars are drawn toward the center, but they do not plunge in chaotically. Instead, the black hole's immense gravity forces them into orderly, predictable orbits around the central void. This maintains the orbital integrity of the entire central stellar population, preventing the kind of large-scale distortions that could warp the galaxy's core or scramble its beautiful spiral pattern. Think of it as a massive, invisible plumb bob hanging at the center of the galaxy, ensuring that no matter what gentle rain of stars falls in from the outskirts, the very heart of the system remains balanced and true. In giant elliptical galaxies like M87, this effect is profoundly clear. M87 has a history of consuming smaller companions, yet its smooth, featureless elliptical shape remains perfectly intact, largely thanks to the gravitational dominance of its central black hole, one of the most massive ever detected. This black hole acts as the ultimate cosmic guardian, its gravity providing a point of serene stability around which the entire galaxy can quietly evolve. But its role is not purely gravitational. These central engines can also produce powerful feedback. When a supermassive black hole actively feeds on gas, it can unleash tremendous outflows of energy, known as active galactic nuclei feedback. These cosmic winds blast outwards, heating surrounding gas and preventing it from collapsing to form new stars. In the context of a minor merger, this is a crucial regulatory mechanism. Even if a small satellite galaxy brings a wisp of gas with it, the black hole's feedback can heat or expel that gas before it has a chance to collapse and trigger a disruptive burst of star formation. It ensures the meal remains a quiet one without the brilliant, chaotic fireworks that would otherwise leave a permanent scar on the host galaxy. This dual role as both a gravitational anchor and a regulator of star formation cements the supermassive black hole's place as a master of cosmic order. Its silent work at the galaxy's core enables a grander process, a pattern of growth built from the bottom up through the steady accumulation of smaller systems. This cumulative growth is the universe's ultimate recipe for building giants. Galaxies do not typically form in a single, violent birth. They assemble themselves piece by piece over billions of years through a process astronomers call hierarchical merging. It is a cosmic strategy of slow, steady accumulation, where a central galaxy feasts on a long sequence of minor satellites rather than facing one catastrophic collision. Each of these small absorption events is so minor on its own that it barely registers. The incoming mass is a tiny fraction of the host's total, and the gravitational energy released is negligible. Because each event is so insignificant, the galaxy has ample time to dynamically relax and settle back into equilibrium before the next small meal arrives. The overall effect is not a series of disruptive shocks, but a remarkably smooth and gradual increase in size. Picture a great oak tree growing over centuries. Each year, it adds a new, thin ring to its trunk. The tree becomes larger and more massive, yet its fundamental shape, the spread of its branches, and its majestic silhouette remain recognizably the same. This is precisely how a spiral galaxy can grow without losing its iconic arms. It simply adds stellar rings to its history, one quiet merger at a time. Grand cosmological simulations like the Eagle Project vividly demonstrate this principle. They model the entire universe in a computer, tracing the evolution of millions of galaxies from the early cosmos to the present day. These simulations consistently show that galaxies which experience a history dominated by minor mergers are the ones that most successfully preserve their initial type. A spiral galaxy that grows by patiently absorbing dwarfs will likely remain a spiral for most of its life. The evidence for this gradual assembly is not just in the simulations, it is written in the faint light of the galaxies themselves. Look beyond the bright disk into the sparse stellar halo that surrounds every major galaxy. This halo is the Galactic Archive, a vast repository of cosmic history. Here, sophisticated telescopes and surveys like Gaia do not see a smooth, uniform distribution of stars. Instead, they map intricate, faint streams and clouds of stars, the ghostly debris of long-vanished dwarf galaxies. These stellar streams are the fossilized records of past meals, the final, shimmering traces of galaxies that were quietly dismantled and assimilated. They are the proof of a step-by-step growth process that preserves the central pattern, a testament to the universe's preference for patience over violence. This hidden history of quiet acquisition compels us to ask how we can possibly read these ancient stories written in starlight. The faintest light around a galaxy tells the deepest stories. Modern telescopes, armed with digital eyes far more sensitive than our own, have begun to read these subtle narratives in the night sky. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, and in their painstaking analysis, astronomers found something extraordinary. Around a beautiful spiral known as NGC 5907, they discovered a breathtakingly faint loop of stars, a delicate ribbon of light wrapping around the galaxy's bright disk. This stellar stream is the ghost of a dwarf galaxy, completely dismantled in a merger that concluded long ago. and yet the spiral pattern of NGC 5907 remains perfectly sharp and undisturbed. This is not an exception, it is a common signature. These faint halos and streams are the ultimate evidence that a galaxy can grow through consumption while keeping its iconic form perfectly intact. To understand how this is possible, we must turn from the telescope to the supercomputer. Hydrodynamical simulations are virtual universes, complex models that account for the pull of gravity, the flow of gas, and the birth of stars. Within these digital realms, astronomers can reenact galactic collisions with incredible precision. They can set the initial conditions, adjusting the mass ratio, the orbital angle, and the amount of gas in the smaller galaxy. They then run the simulation forward in time, watching as the event unfolds over billions of years of compressed processing time. What these simulations reveal is a clear set of rules. They show that when a small, gas-poor galaxy approaches on a wide, prograde orbit, the result is almost always a pristine host galaxy adorned with faint tidal streams, a perfect match for what we see around NGC 5907. The simulations act as a cosmic laboratory, allowing us to isolate the exact parameters that lead to a silent feast rather than a violent transformation. This powerful combination of deep observation and sophisticated simulation has fundamentally changed our understanding of galactic life. A galaxy that looks static and unchanging in a single photograph is, in truth, a dynamic entity with a rich history of quiet acquisition. Its beautiful shape is not a sign of a peaceful life, but rather the signature of a particular style of growth, one built from the bottom up through countless minor mergers. This knowledge forces us to look closer to home and consider the ultimate fate of our own cosmic neighborhood, as the Milky Way and Andromeda continue their silent, gravitational dance. Our own galactic home is a living testament to this quiet consumption. The Milky Way is not a static island universe but an active cannibal, currently in the process of absorbing multiple dwarf galaxies. The most prominent of these is the Sagittarius dwarf spheroidal galaxy, a tiny companion being methodically torn apart by our galaxy's immense gravity. Sophisticated maps from the European Space Agency's Gaia mission reveal the ghostly evidence of this feast. They show the Sagittarius stream as a vast, shimmering river of stars wrapping around the Milky Way, a celestial ribbon slowly dissolving into our galactic halo. Yet, when we look up at the night sky, the grand architecture of the Milky Way's spiral arms remains perfectly clear and undisturbed. Why does this dramatic dismantling leave our home so unscathed? The answer lies in the perfect storm of conditions we have explored. The mass ratio is overwhelmingly in our favor, with the Milky Way thousands of times more massive than the Sagittarius dwarf. This tiny galaxy is also gas-poor, a collection of ancient stars that offers no fuel for disruptive starbursts. Its orbit is wide and gradual, allowing tidal forces to do their slow, delicate work far from the vulnerable disk. This real-time example provides a nearby laboratory, confirming that the theoretical principles of pattern preservation are not just abstract ideas, but are actively shaping our cosmic neighborhood. The Milky Way's resilience demonstrates the delicate balance required for a galaxy to grow through silent feasts. This very stability, however, forces us to confront its violent opposite. What happens when the cosmic scales are more evenly balanced and a meal becomes a catastrophic collision? Our galaxy's serene growth stands in stark contrast to the cosmic violence that occurs when equals meet. A major merger, the collision of two galaxies of similar size, is a catastrophic event that reshapes their destinies. The future collision between our Milky Way and the Andromeda Galaxy is the ultimate local example. In about 4 billion years, these two great spirals will swing past each other, their gravity violently distorting their beautiful disks into long, shimmering tidal tails of stars and gas. They will then fall back together, plunging through one another not once, but several times in a chaotic dance lasting hundreds of millions of years. During this turmoil, a process called violent relaxation takes hold. The complex, shifting gravitational fields act like a cosmic blender, completely randomizing the orderly orbits of billions of stars. The delicate, rotating disks of both galaxies are utterly shredded. The elegant spiral patterns dependent on that flat, orderly rotation are erased forever. What emerges from the chaos is not a larger spiral, but a new type of galaxy altogether, a giant elliptical. This new galaxy will be a vast, formless cloud of stars buzzing in every direction, a testament to the incredible destructive power of an equal merger. The presence of gas makes these events even more spectacular. When two gas-rich spirals collide, their vast clouds of hydrogen slam together under immense pressure. This triggers ferocious starbursts, igniting the birth of millions of new stars all at once. The brilliant blue light of these young stars can outshine the entire galaxy, and the subsequent supernova explosions blast material outward, further churning and reshaping the remaining gas. These are the universe's most intense fireworks, but they leave behind a permanently altered landscape, often creating new structures like bright central rings or dramatically puffed-up stellar distributions. Observing these violent transformations, like the famous antennae galaxies in the midst of their collision, helps us appreciate the precise conditions for a peaceful meal. The key difference is not the act of merging itself, but the balance of power. A major merger is a battle between near equals, a gravitational war where neither side's structure can survive. A minor absorption, however, is a total surrender to an overwhelming force, a quiet assimilation where the dominant galaxy's structure remains in complete control. This dramatic contrast underscores why the invisible scaffolding of dark matter is so vital, as its immense halos ensure that most encounters are lopsided affairs, not fair fights. That dark matter halo does more than just cushion the blow, it undergoes its own silent transformation. As a satellite galaxy is pulled into the embrace of a giant, its own small halo of dark matter, what astronomers call a subhalo, faces a relentless assault. The host galaxy's immense gravitational field acts like a cosmic tide, tearing at this invisible structure. The subhalo is gradually stripped of its outermost particles, which are pulled away and diluted into the vast, formless expanse of the host's primary dark matter halo. This process is profoundly different from what happens to stars. Stars can collide, their gas can compress and ignite, but dark matter particles barely interact with each other at all. They simply pass through one another like ghosts in the night. So as the subhalo is torn apart, its dark matter doesn't clump or crash. It just disperses, spreading out smoothly and adding its mass to the background gravitational field of the host. This is a quiet fading, not a violent end. Sophisticated computer simulations trace the life and death of these dark matter subhalos. We see that they can survive for billions of years as distinct, albeit weakened, clumps within the larger halo. But their gravitational influence becomes so diffuse, so spread out, that they cannot exert a concentrated pull on the bright, swirling disk of stars at the galaxy's heart. The satellite's dark matter contributes to the host's total mass, making its gravitational well slightly deeper, but it does so without leaving a single fingerprint on the luminous structure we observe. This is the ultimate decoupling of dark and ordinary matter. The stars of the consumed galaxy are tidally shredded into faint streams, while its dark matter simply evaporates into the invisible background. One component leaves a faint archival trace, while the other vanishes without a whisper. This silent fading of the dark matter subhalo is a fundamental reason the galaxy's beautiful pattern can endure such a cosmic meal, a process that highlights how the visible universe is shaped by forces we can never directly see. Even the galaxy's magnetic fields are powerless to disrupt this serene feast. We often think of magnetism as a powerful, invisible force, but on the galactic scale, its influence is surprisingly subtle. While these vast magnetic fields do help shape the birth of new stars and guide the flow of cosmic rays, they are simply too weak to alter the grand ballet of a galactic merger. The primary force governing the motion of stars is gravity, and its pull is millions of times stronger than any magnetic pressure a galaxy can muster. Picture a handful of iron filings tossed into a hurricane. The storm's immense wind, representing gravity, will dictate exactly where those filings go, completely overwhelming the tiny magnetic attraction between them. The same is true for stars being assimilated from a dwarf galaxy. Their paths are governed entirely by the deep gravitational well of the larger galaxy, with magnetic fields offering no meaningful resistance or guidance. This becomes especially clear in the quietest mergers of all, those involving gas-poor dwarf galaxies. Magnetic fields are intrinsically tied to ionized gas, the same material that is conspicuously absent in these cosmic fossils. With no gas to act as a carrier, the magnetic field has no medium through which to exert any force on the incoming stars. The entire absorption process unfolds within a purely gravitational realm, leaving the host galaxy's own magnetic architecture completely untouched. Its large-scale field lines remain woven through the disk undisturbed, another invisible system that endures the meal without a flicker. This gravitational dominance is so absolute it even governs the slow, steady orbital decay of the victim itself through a process known as dynamical friction. This slow inward spiral is choreographed by a hidden cosmic force known as dynamical friction. It is the universe's gentle brake, ensuring a satellite galaxy's descent is a gradual waltz rather than a fatal plunge. As the smaller galaxy moves through the host's vast, diffuse halo of dark matter and sparse stars, it doesn't travel unimpeded. Its gravity tugs on the particles and stars it passes, creating a slight gravitational wake behind it, like a boat moving through water. This wake exerts a subtle but constant drag, pulling back on the satellite and steadily sapping its orbital energy and angular momentum. The satellite loses speed, causing its orbit to decay, slowly spiraling closer to the heart of the giant. In a violent, equal mass merger, this process can be rapid and catastrophic, hurling the galactic cores together. But in the case of a minor merger, the timescale is stretched to the extreme. Because the mass ratio is so lopsided, the drag force is incredibly weak. The satellite is like a tiny pebble sinking through a vast vat of honey, taking billions of years to reach the bottom. This immense duration is the key to pattern preservation. The slow orbital decay gives tidal forces all the time they need to work. With each leisurely loop around the host, the satellite is stripped a little more, its stars peeled away and seamlessly blended into the halo long before the core could ever make a disruptive run at the delicate disk. The host galaxy does not experience a sudden gravitational shock. Instead, it adjusts to the slowly increasing central mass with a smooth, adiabatic response, its stars gently shifting to new, stable orbits without any collective turmoil. This prolonged, gentle decay means the absorption is not a single event, but a drawn-out process of assimilation so slow and steady that the galaxy's iconic structure remains perfectly intact, its beautiful form undisturbed by the quiet feast happening in its outermost reaches. This elegant, energy-sapping dance sets the stage for the final act of regulation, where the galaxy itself activates mechanisms to prevent any last-minute chaos. A galaxy must remain quiet to keep its shape. The absence of violent feedback is the silent guardian of its structure. In a gas-rich merger, the chaos is not just from the collision itself, but from the furious response it triggers. When vast clouds of gas slam together, they ignite a firestorm of new star birth. These starbursts create massive, hot stars that live fast and die young, exploding as supernova. Each supernova blast is a tremendous outburst of energy, driving powerful winds that can heat the surrounding gas to millions of degrees and even blow it clear out of the galaxy. This stellar feedback churns the interstellar medium, the galaxy's raw material for future stars, scattering it and permanently altering the gravitational landscape of the disk. It is a self-inflicted wound that reshapes the galaxy from within. But in the quiet absorptions we have been exploring, this entire cycle is absent. The consumed dwarf galaxy is gas-poor, a dried-out fossil. With no fresh gas to compress, there is no starburst. Without a starburst, there are no supernova to drive violent winds. The interstellar medium of the host galaxy remains calm and undisturbed, its delicate balance intact. This lack of internal feedback means the galaxy's gravitational potential, the shape of its gravitational well, remains perfectly stable. Stars continue on their ancient orbits without being jostled by sudden pressure waves or expanding bubbles of hot gas. Their distribution is not perturbed, and the beautiful density waves that create spiral arms can continue their slow, graceful rotation without interruption. We see this most clearly in evolved galaxies, often massive ellipticals or old spirals, where the era of rapid star formation has long since passed. These galactic seniors have settled into a quiet life, and when they absorb a small companion, they do so without triggering any new disruptive activity. The meal concludes without a single cosmic burp. This profound quiet is not an accident, but a fundamental condition that points toward the deep history of our universe, and how the very nature of galaxy formation set the stage for these silent feasts to become the preferred method of growth. A galaxy's deep past writes the rules for its peaceful consumption. The formation history of a cosmic giant is the ultimate determinant of its resilience, a story locked in the age and composition of its stars. Galaxies that assembled early in the universe, undergoing a rapid initial burst of growth, forged incredibly stable structures from the start. They built deep gravitational wells and evolved quiescent stellar populations that act as a buffer against later disturbances. These ancient galaxies are the universe's seasoned aristocrats, their fundamental dynamics so firmly established that the arrival of a tiny dwarf galaxy is a trivial event, a minor ripple in a vast settled pond. In contrast, a younger galaxy still actively forming stars is a more chaotic and vulnerable place. Its gravitational potential is still shifting, its gas reservoirs are turbulent, and its stellar populations are dynamically hot. A minor merger for such a galaxy can be like throwing a rock into a pond already churned by wind. It can trigger disproportionate and lasting disruptions. Astronomers read these life stories by analyzing starlight itself. They measure the metallicity of stars, the abundance of elements heavier than hydrogen and helium. Stars born early in the universe's history, in small protogalaxies, have very low metallicity. When a giant galaxy is surrounded by a halo rich with these ancient, metal-poor stars, it is a clear sign of a formation history dominated by the quiet accretion of countless small building blocks. This historical perspective reveals that pattern preservation is not a lucky accident, but a mark of cosmic maturity. It connects the silent feasts of the present directly to the violent assembly line processes of the early universe, forcing us to widen our gaze from individual galaxies to the grand architecture of the cosmos itself. This quiet mode of growth is the universe's preferred method of construction. Across the vast expanse of space and time, the serene absorption of smaller galaxies is not a rare exception but the standard rule for how giant galaxies mature. We live in a special cosmic era for this very process. In the early universe, galaxies were packed closer together, and violent, major collisions that scrambled shapes were far more common. But as the universe has continued its relentless expansion, galaxies have been carried farther apart. Encounters are now less frequent, and when they do happen, they are far more likely to be these lopsided affairs, a giant meeting a dwarf. This shift in frequency is crucial. It means that in the present-day cosmos, pattern preservation has become the dominant outcome of galactic interactions. The grand spiral we see in a distant galaxy is not a survivor from a peaceful void. It is the product of a history filled with quiet, successful feasts. This entire narrative of bottom-up growth is the central prediction of our most successful model of the universe, known as the Lambda-CDM model. This framework tells us that the cosmos and all its structures built themselves from the ground up. Small clumps of dark matter merged to form larger ones, which then attracted gas to form the first stars and tiny galaxies. Over billions of years, these small galaxies were drawn into the gravitational wells of larger ones, steadily building the majestic spirals and ellipticals we see today. The model expects that massive galaxies should be surrounded by the faint, digested remains of their many smaller companions, and with our most powerful telescopes, that is exactly what we find. This cosmological context transforms our understanding. Every pristine, beautiful galaxy with a clear spiral pattern is not a static portrait. It is a living testament to a specific history of hierarchical growth, a history written in the faint light of its halo. Yet for all its predictive power, this grand framework forces us to confront a profound and simple limitation. We are seeing only a single frame in a movie that has been playing for billions of years. Our current view of the cosmos is fundamentally limited by the sensitivity of our instruments. We gaze upon a beautiful spiral galaxy and see a pristine, untouched structure, but that impression might be a grand illusion of scale. The faintest stellar streams, the most subtle evidence of a past meal, often lie just below our current detection threshold. This means we could be dramatically underestimating how often these silent feasts occur. Many of the galaxies we classify as isolated and peaceful may, in fact, be seasoned cannibals, their histories of consumption written in ink too faint for our telescopes to read. This observational blind spot is on the verge of vanishing. A new generation of observatories is poised to revolutionize our view. The James Webb Space Telescope, with its profound infrared sensitivity, will peer through cosmic dust to uncover the oldest and most faded stellar streams, tracing the ghostly remains of the first galaxies ever consumed. Meanwhile, the Vera C. Rubin Observatory, with its colossal camera, will repeatedly scan the entire southern sky, detecting changes in the faintest light around millions of galaxies. It will map the delicate, wispy trails of dissolving dwarfs on a scale never before imagined. What will this new data reveal? It is entirely possible that we will find these stellar streams to be as common as cobwebs in a cosmic cellar. The beautiful spiral patterns we admire may almost always be set against a background of faint, shimmering debris, the unmistakable signature of a quiet history of growth. This would transform pattern preservation from a curious cosmic anomaly into the standard rule for how mature galaxies evolve. The mystery deepens precisely as our vision improves, a humbling reminder that every answer unveils new questions. With our observational frontier expanding so dramatically, the theoretical models of galaxy formation face their ultimate test. These theoretical models are more than just digital recreations, they are virtual time machines. Astrophysicists use powerful n-body simulations and complex hydrodynamical codes to rewind and fast-forward cosmic history, testing the very conditions that lead to a silent feast. Within these digital universes, they can hold one factor constant while tweaking another, isolating the precise recipe for pattern preservation. They might set a massive spiral galaxy as the host, then send a tiny, gas-poor dwarf toward it on a wide, prograde orbit. When they run the simulation, the result is exactly what we see in the real cosmos. The dwarf is tidally shredded into faint streams while the spiral's grand design remains perfectly sharp. This is a powerful confirmation, but then they change a single variable, perhaps giving the dwarf a retrograde orbit or a significant amount of gas. Instantly, the outcome shifts toward chaos, with the spiral's disk warping or erupting in starbursts. It is through thousands of these virtual experiments that the rules become clear: the overwhelming importance of mass ratio, the calming influence of a prograde approach, and the critical role of a gas-poor diet. The stunning agreement between what these simulations predict and what our telescopes actually observe gives us immense confidence. We are not just guessing, we are reconstructing the physics of galactic life with remarkable precision. This robust framework, where theory and observation constantly inform each other, paints a coherent and dynamic picture of how galaxies evolve. Yet, for all its success, this very framework is challenged and refined by the exceptions, the cosmic outliers that refuse to follow the rules. Even the most elegant rule has its fascinating exceptions. While the vast majority of galactic meals leave no visible trace, a few curious cases reveal subtle scars. Look closely at a galaxy like NGC 2686, and you might detect a faint integral sign warp at the very edge of its disk. This delicate bending is the ghostly signature of a past minor merger, a distortion that did not fully heal. Such anomalies typically arise when the incoming satellite galaxy strikes a resonant chord with the host. If the dwarf's orbital period synchronizes with the natural oscillation frequency of the larger galaxy's disk, its gravitational tug can amplify these tiny vibrations, creating a persistent warp or a faint ripple in the outer stellar population. The satellite does not need to be large, just musically attuned to the galaxy's own structure. This is a gravitational resonance, a cosmic example of a singer shattering a glass with the perfect note. The satellite's relatively small mass is still enough to hit that resonant frequency, leaving a localized imprint without destroying the overall spiral pattern. These edge cases are not failures of our theories but refinements. They show that pattern preservation is a spectrum. A galaxy can absorb a dozen dwarfs flawlessly, but the 13th, with just the right mass and orbit, might leave a faint, lasting whisper in the outer disk. This nuanced view deepens our appreciation for the delicate balance of galactic dynamics. If a relatively small amount of mass in the right place can cause a detectable warp, it forces us to look at the environment within the disk itself, at the very fabric that might transmit these distortions. This leads our inquiry inward to the role of the interstellar medium, the thin gas that fills the space between the stars. The thin gas between the stars is the galaxy's final line of defense. This interstellar medium, a diffuse sea of hydrogen and dust, can either absorb a merger's violence or remain perfectly still. In the quiet feasts we have been exploring, its role is one of profound calm. When the consumed dwarf galaxy is gas-poor, it brings no fresh fuel to the encounter. There is no violent slam of gas clouds, no shattering shock waves racing through the disk, and no sudden compression to ignite frantic waves of new stars. The host galaxy's own interstellar medium simply isn't provoked. It remains a placid, undisturbed pool, and because this gas is the raw material for future generations of stars, its tranquility guarantees the galaxy's future stability. The beautiful spiral density waves, which rely on a delicate balance of gravitational forces within this gaseous disk, can continue their slow, majestic rotation without interruption. This is the ultimate non-interaction, a meal that leaves the kitchen completely clean. Now consider the violent alternative. When a gas-rich satellite plunges in, the result is a spectacular mess. The incoming gas smashes into the host's galactic disk, compressing vast clouds in an instant. This triggers a firestorm of star birth, often forming brilliant ring structures or a blazing central starburst that can outshine the entire galaxy. These events are visually stunning, but they are also profoundly disruptive. The intense radiation and subsequent supernova explosions from all these new stars blast outwards, churning the interstellar medium and permanently altering the gravitational landscape of the disk. The galaxy's morphology, its very shape, is often rewritten. This dramatic difference highlights why the interstellar medium's quiet nature is so critical. It acts as a buffer, but only if it is never activated. The energy budget of the entire merger remains negligible because the gas, the component most capable of converting gravitational energy into light and chaos, simply refuses to participate. The serene assimilation of stars can proceed without this internal combustion engine ever turning over, allowing the galaxy's iconic pattern to persist through a meal that, on paper, should have been a catastrophe. The satellite galaxy's energy simply vanishes into the void. When a small galaxy is consumed, it carries kinetic energy from its motion, a tremendous force that could, in theory, tear the larger galaxy apart. But this energy does not simply disappear. It is meticulously dissipated through two cosmic mechanisms. Dynamical friction acts as a universal brake, sapping the satellite's orbital energy as it plows through the host's diffuse halo. Simultaneously, tidal interactions stretch and pull the dwarf apart, converting its cohesive energy into the random motion of its own individual stars. This dual process does not create chaos at the center. Instead, the energy is thermalized. Think of it as dropping a single hot coal into a massive, cold lake. The coal sizzles and cools, its heat spreading so thinly throughout the immense volume of water that the overall temperature of the lake does not even flicker. In the galactic context, the lake is the vast, spherical halo of dark matter and sparse, old stars that surrounds the bright disk. The satellite's energy is deposited there, in the galactic outskirts, where it dissipates harmlessly. This prevents any localized heating in the sensitive, thin disk where stars orbit in orderly paths. If that same energy were concentrated in the disk, it would act like a shock wave, violently puffing it up and randomizing stellar orbits, ultimately erasing the beautiful spiral pattern. Because the energy is spread over such a colossal volume in the halo, the host galaxy's internal energy distribution remains perfectly balanced. The delicate gravitational dance that maintains the spiral arms continues uninterrupted, completely oblivious to the violent end of the dwarf galaxy in its outer reaches. This efficient cosmic ventilation system is why these absorptions leave so little trace. It allows a galaxy to gain mass and energy without ever breaking a sweat, a silent thermodynamic miracle that preserves its iconic face. This very principle opens a door to galactic archaeology, where we read the energy signatures of past events to reconstruct a galaxy's hidden history of quiet feasts. These faint stellar streams are more than just cosmic debris. They are a galactic fossil record. The sparse halo of stars surrounding every major galaxy is its personal archaeological site, a deep time archive of every quiet meal it has ever consumed. Astronomers have become cosmic detectives, practicing a field known as Galactic Archaeology. By carefully mapping the motions, compositions, and ages of stars in the halo, they can dig backward through time to reconstruct a galaxy's complete merger history. They are not just looking at a static picture, they are reading a dynamic biography written in starlight. Our own Milky Way provides the most detailed case study. Its halo is not a smooth, uniform sphere. It is a tangled web of stellar streams, the shredded remains of dozens of dwarf galaxies that were slowly torn apart and assimilated. The Gaia spacecraft has mapped these structures with stunning clarity, revealing ghosts like the Gaia Sausage and the Sagittarius stream. Each of these is a chapter in our galaxy's life story, a testament to a past absorption. And the crucial point is this: despite this long and violent history of consumption, the Milky Way's magnificent spiral pattern remains perfectly clear and intact. The archaeological evidence proves that growth and pattern preservation are not mutually exclusive. In fact, they go hand in hand. The halo tells the story of quiet accumulation, while the pristine disk is the living result. This detective work relies on subtle clues. Stars that form together in the same dwarf galaxy share a unique chemical fingerprint, a specific ratio of elements that acts like a cosmic passport. When astronomers find a group of stars in the halo with the same unusual chemistry and a shared, distinct motion, they know they have identified the remains of a single, long-vanished galaxy. By tracing these groups, they can even estimate when the merger occurred, building a timeline of our galaxy's growth. This ability to read the cosmic fossils in the halo fundamentally changes our understanding of galactic evolution. It confirms that the beautiful structures we see are the endpoints of a specific, gentle style of growth, a history written not in violent collisions, but in the slow, steady digestion of countless smaller neighbors. This deep historical view, however, inevitably turns our gaze toward the future and the ultimate fate that awaits our own galactic home. Looking ahead, we can map the future of galactic cannibalism with surprising confidence. The rules we have uncovered form a predictive framework, allowing astronomers to identify which galaxies are destined to grow through silent feasts and which might face a more chaotic transformation. In the dense cores of galaxy clusters, the future is one of quiet, relentless accumulation. Giant elliptical galaxies, like the one at the heart of the Virgo cluster, will continue to act as cosmic sponges. They will steadily absorb the many gas-poor, pre-processed dwarf galaxies that orbit them, their smooth, featureless shapes growing ever so slightly larger without a single visible change. Their environment guarantees a steady diet of subdued, easily digested companions. In the quieter cosmic countryside, isolated spiral galaxies face a different fate. Many will continue their serene existence, occasionally capturing a small, wandering dwarf. If the merger follows the golden rules, a wide orbit and a significant mass difference, the spiral's magnificent disk and arms will persist, its beauty untouched by the slow assimilation happening in its outer halo. But not every future meal is so clear-cut. Our own Milky Way provides a fascinating and imminent test case. The Large Magellanic Cloud, our most massive satellite galaxy, is on a collision course with us. This is not a simple, lopsided feast. The Large Magellanic Cloud is relatively massive and, crucially, still gas-rich. Its impending merger will push the limits of pattern preservation. Will our galaxy's immense gravity and dark matter halo be enough to smoothly dismantle this larger, more vibrant companion without scarring the spiral disk? Or will the infusion of fresh gas trigger starbursts and subtle distortions? This real-world event will be a crucial laboratory, testing our simulations against reality. The predictions from those virtual universes are precise. They suggest that while the merger will be more dramatic than the consumption of the Sagittarius dwarf, the Milky Way's spiral structure will likely endure, though its halo will be profoundly reshaped. The ultimate validation will come from future observatories. The Vera C. Rubin Observatory and the James Webb Space Telescope will watch these cosmic predictions unfold in real time across the universe, monitoring distant galaxies as they engage in their own quiet feasts. They will provide the data that refines our models, perhaps revealing new, subtle conditions for pattern preservation we have not yet even considered. The future of galactic cannibalism is not a mystery, but a set of probabilities written in the current properties of galaxies and their environments. A forward-looking science that confirms these silent feasts are the enduring rhythm of cosmic evolution. These universal principles are not arbitrary rules. They are the bedrock of cosmic behavior, governing everything from a falling apple to a devouring galaxy. At the heart of this serene consumption lies the virial theorem, a profound concept that describes how gravitational systems seek a balanced state between their kinetic energy and potential energy. In simpler terms, it's the universe's way of ensuring that a system doesn't fly apart or collapse in on itself, but finds a stable, middle ground configuration. When a massive galaxy absorbs a tiny one, the energy from that event is so insignificant compared to the host's total energy budget that the system effortlessly re-establishes this balance. The galaxy simply settles back into its preferred equilibrium, its shape preserved because the fundamental energy relationship was never truly challenged. Alongside this, tidal forces act as the universe's precise surgical tool. Their gentle, persistent pull works over immense timescales, not to shatter, but to carefully dismantle. They strip the smaller galaxy apart in the halo, far from the delicate disk, allowing the main structure to remain dynamically cold and ordered. Because these principles are written into the fabric of spacetime itself, they operate with perfect consistency from one end of the cosmos to the other. A spiral galaxy in the Virgo cluster, another in the distant Hubble Deep Field, both obey the same gravitational laws. This means the silent feasts we observe in our own Milky Way are not a local oddity, but a standard chapter in the life story of galaxies everywhere. The elegant dance of gravity ensures that across billions of light years, majestic spirals can grow by consuming their neighbors while retaining their iconic beauty, a testament to the universal and predictable nature of the cosmos. This grand perspective, where immense structures are shaped by simple, consistent rules, inevitably makes our own fleeting view of the universe feel both humbling and profoundly illuminating. We gaze at a spiral galaxy and see a perfect frozen pinwheel, but this is a cosmic sleight of hand. The serene beauty we observe is a snapshot of an active and dynamic life, a system constantly feeding and growing. Its stable appearance is not a sign of stillness, but the product of a specific, gentle style of growth we have been exploring. The majestic spiral pattern endures precisely because the galaxy is an expert cannibal, absorbing smaller neighbors in a way that leaves no visible scar. This creates a profound disconnect between what we see and what is truly happening. We perceive a timeless portrait, while the galaxy is living a biography of quiet acquisition. This is the grand illusion of galactic permanence. Stability in the cosmos is not a passive state of being left alone. It is an active, hard-won condition. It is the result of a perfect storm of physical laws, from the cushioning effect of dark matter halos to the graceful choreography of prograde orbits. A galaxy maintains its iconic shape not by avoiding violence, but by managing it with such overwhelming force and patience that the violence becomes invisible. Uncovering the faint stellar streams and hidden merger histories shatters the illusion. It reveals that the universe is not filled with static islands, but with dynamic entities engaged in a slow, relentless dance of construction. This realization transforms our entire perspective. The cosmos is not a museum of fixed exhibits. It is a living, breathing engine of growth, where the most beautiful and stable forms are often the most voracious and active. This intricate balance is the universe's recipe for cosmic preservation. No single factor, no matter how powerful, can by itself ensure a galaxy's pattern survives a merger. The overwhelming mass disparity is vital, but without the dark matter halo to act as a gravitational cushion, even a lopsided collision could send disruptive ripples through the disk. A perfect prograde orbit is essential, yet if the incoming galaxy is rich in gas, that graceful approach would still end in a brilliant, chaotic starburst. Each condition supports the others, creating a robust and resilient system. Think of it as a masterfully designed suspension bridge. The strength of the bridge does not come from a single cable or tower, but from the precise interplay of every component. If one cable snaps, the entire structure is compromised. In the same way, a galaxy that possesses all these traits, a massive dark matter halo, a vast size advantage, a gas-poor diet, and a harmonious orbital approach, builds a structural integrity that can withstand the gravitational stress of consumption. This synergy is what allows for seamless integration. The incoming stars are not just added, they are incorporated. They find their place within the existing orbital architecture, their motion aligning with the galaxy's own rhythm so perfectly that the overall dance remains unchanged. This synthesis reveals that a galaxy's iconic shape is not a fragile artifact, but a dynamic equilibrium. It is a state of balance actively maintained by a chorus of physical laws, a form of cosmic resilience that allows these islands of stars to grow and evolve while holding onto the beautiful identity we see from afar. The universe prefers this gentle method of construction, a quiet accumulation that builds giants without ever breaking their beautiful forms. Our journey through the silent feasts of galaxies reveals a universe built on gentle accumulation. We have uncovered the invisible architecture that makes it possible, from the gravitational cushion of dark matter halos to the precise choreography of orbital dynamics. These are not violent collisions but serene assimilations, where overwhelming mass and patient tidal forces work in concert to preserve a galaxy's iconic beauty. This process challenges our most dramatic instincts about the cosmos, showing us that the most profound growth often happens in whispers, not in crashes. The next time you look up at a spiral galaxy gracing a telescope image, remember that its perfect form may be the signature of a quiet cannibal. Its majestic arms and brilliant core have endured not by avoiding conflict, but by consuming countless smaller neighbors with such grace that it leaves no trace. This hidden history of cosmic consumption is actively shaping the universe we observe today, building the giants that will one day collide in the far future. Our understanding is always evolving, and with powerful new telescopes coming online, we stand on the brink of even greater revelations about how galaxies live and grow. If this voyage into the heart of cosmic mysteries captivated you, subscribe for more journeys to the edges of our understanding. Let us know in the comments which space mystery you would like to explore next. The universe is an endless source of wonder, and there are always more stories written in the stars waiting for us to read